Hello, everyone, and welcome to Transformation is Strategy, a podcast brought to you by the experts at Roland Berger Americas, where we explore fresh perspectives and practical strategies to help business owners create a lasting competitive edge. I'm your host, Mackenzie Puddesy, and the topic for this episode is energy storage at AI data centers. Joining me for today's conversation is Spencer Gore, partner at Roland Berger. Hello, Spencer. Welcome to the show.
Hey, Mackenzie. Thanks for having me.
Yeah, no, my pleasure. I'm excited to dig into this topic with you. So Spencer, it seems like every day a new AI data center is announced. And I want to ask you, how are these AI factories different from traditional cloud data centers? And how do these differences change the demand for power?
Absolutely. It's a great question. So first of all, it's important to distinguish there are two different types of AI data centers. We have facilities that are predominantly focused on training new models. And then there are those which are performing inference. Inference is the service that when you use ChatGPT, you're calling on some servers to perform inference on a model that's already been trained. So start with training. The AI training workload is unlike anything else that we've ever deployed at scale. What's essentially happening when you train a new large language model is that you're taking hundreds of terabytes of data, breaking it apart into small chunks, feeding it out to hundreds of thousands of GPUs, which then perform simultaneous calculations to try to slightly tweak the weights in a model. What that looks like in practice is GPUs going through sort of a breathing cycle. So first, they perform what's called a forward pass of calculations, generating some predictions. They then perform a backward pass, which computes some gradients on how to improve. And then they go through what's called an optimizer step, in which the gradients they calculated are shared with all of the other GPUs. They update the model weights, and then they do it all over again. That cycle can take somewhere between maybe a few seconds, maybe a couple minutes. It really depends on the size of the model. And the facility's power consumption changes dramatically during those different phases. Because, for example, during the backward pass, this is a very computationally heavy, tensor math filled step. But during the optimizer step, you're more memory bound. And so if you actually watch the power consumption of the facility, you'll see it essentially follow kind of a sawtooth wave during training as it moves from one phase to the next. Now, the duration of these phases is, changes depending on the model architecture. But the short answer is that AI training creates highly synchronous variable power loads. And that's the source of the problem that batteries are being called on to solve. AI inference, on the other hand, so once the model's already trained, looks quite a bit more like a traditional cloud computing load. The GPUs are not acting all simultaneously. They're serving different prompts as they come in. Instead, the variability is a little bit more like you would expect for traditional cloud services. So there might be peaks in the middle of the day when everybody's logged into Cloud Code, and then valleys overnight. And so very different types of loads that ultimately drive different types of power challenges at the data center, and then correspondingly have different requirements for energy storage.
Spencer, perfect. I think you really laid that out clearly, and I loved even just visualizing those graphs in my head of how the power has been consumed and moving. It sounds like there's inherent variability in these workloads. So beyond that, are there other power challenges faced by training data centers?
Absolutely. So there's the source of variability that we just discussed, which is every time there's a forward or backward pass in the model weights, the data center power consumption changes. But there are also effects that occur on longer timescales. For example, usually at the end of every training epoch that might happen every couple of hours, traditionally, the model saves its most recent weights to disk. This is called a checkpoint. And during that checkpoint, when you're transferring sometimes hundreds of terabytes to disk, the GPUs might be inactive, just as they're waiting for the next epoch to start. Now, this is not the case in all data centers, but some of them are architected this way. And if the data center's power consumption drops from, say, 1 gigawatt to idle, it might be 400 megawatts, for the period of several minutes as that checkpoint takes place, well, that's a loss of several hundred megawatts that has either been passed through to the grid, which we can get into why that's a problem in just a little bit, or has been passed through to on-site generation, which can also create other problems. So there's essentially an infinite ramp rate, a negative ramp rate that can occur during checkpoints. On the flip side, the reason that you're saving these checkpoints is because when you have large numbers of GPUs, the statistical likelihood of a hardware failure is high. And so whenever a single GPU crashes during a training run, you need to stop, reload the most recent checkpoint, and continue on. It might take 10 minutes or more to begin that resumption. And during that time, again, the data center's power consumption has fallen below its steady state average, which can lead to problems with the ramp rate requirements that you've agreed to with your utility. So checkpointing, both the act of saving and then the act of restoring, can create power challenges. That's on top of the challenges that just come with starting a training run. So if you're initializing from idle to full load, the response time of the on-site generators or of your utility is only so fast. Again, this is usually prescribed in your interconnection agreement.
So Spencer, other than batteries and energy storage, what countermeasures are available to data center operators today?
So we have a small collection of countermeasures today that are somewhat effective, but come with real compromises. They involve either reducing the performance of the GPU during ramp up and ramp down periods, essentially modulating the clock speed to smooth the power consumption. This slows down the training run. Or you can create effectively fake work during the downtime, multiplying 0 times 0 a billion times to keep the GPU's power consumption consistently high. The problem with that countermeasure is that it increases the power consumption of the facility materially, and it also makes the GPUs run hotter, which shortens their lifetime. So the best possible solution here is an energy storage device that can simply hold on to the energy when the GPU doesn't need it and then dispatch it when it's time. And that really is why we're talking about batteries.
That's fascinating and a real problem. It sounds like this variability is sort of fundamental to AI training. So, we've got some things now we can do, but what do you expect for these load swings? Are they going to get better or worse in the future?
As we look to the future, there are forces that are driving the trends in both directions. So on the one hand, we have models that are getting larger, greater parameter count, and this tends to increase the duration of both the compute and communication bound periods, which means that essentially the time constants that we're talking about are going to stretch out. On the flip side, as GPUs continue to get faster, memory bandwidth increases, we'll see these periods start to shorten. And so there's a bit of a tension here between hardware and software improvements that will ultimately determine what these power loads are going to look like. At the same time, we're seeing improvements in model architecture. We're predominantly training mixture of experts models today, right? And those present somewhat different power traces back to the facility depending on the parallelization technique that's being employed. And finally, as we start to become more intelligent about how we train these models, for example, performing the optimizer step during the backward pass, therefore skipping the idle time completely, or having checkpointless training, some of these problems may actually go away for certain types of training runs. Which can have very significant benefits for the overall simplicity of the power architecture.
Spencer, I think you've done a really good job giving us a sense of, okay, here are the GPUs, here's how training is working, here's how energy consumption and storage is working today and kind of where it's going. So that gives us a good sense of what's going on in these data centers, in these factories. I'm curious to know, how are utilities responding to these new variable workloads?
Yeah, well, it's a great question, and we're just starting to see it happen now. For many years now, data centers have been getting a free ride exporting their power variability challenges back to the grid, which has a very significant but finite amount of inertia to handle the variability. We're starting to see utilities insist on a few things. First of all, they're beginning to impose ramp rate requirements. So in order to achieve an interconnection, you cannot ramp more than 10 megawatts, 20 megawatts, 30 megawatts per minute, for example. Contrast this with what is physically possible in a data center, which you can ramp a gigawatt in a microsecond. So that's the first driver for the need for energy storage, or ramp rate requirements. Second, limitations around passing back low frequency ripple to the grid. These oscillations that we were discussing before, every 5-10 seconds switching from maximum to minimum power at a data center, it turns out that not only can these resonate with mechanical rotating machines, generators that are attached to the grid, but they can also cause interzonal oscillation. So frequency and voltage excursions happening due to resonance along long transmission lines between two zones in the grid, right? So passing this back above a certain amount to the grid can actually destabilize entire zones and is not being allowed under interconnection agreements. We're also seeing increasing requirements for what is called fault ride-through. So this is when low frequency or low voltage is seen on the grid. Traditionally, a data center would trip, run off of its battery backup, and then wait for grid power to restore to its normal voltage and frequency, and then it would reattach itself. The problem is if you have multiple gigawatts of data center load that are all attached at the same time and trip simultaneously because of a grid fault, then that will actually cause a cascading destabilization of the grid as it can't react to that much load loss instantaneously. And so data centers are increasingly being asked to ride through these grid faults. For example, if the voltage drops 10%, they have to maintain 90% of their load on the grid. And this is another place in which battery storage can be helpful because it can absorb 90% of the data center's load if the data center has decided to trip over to backups. So there are a number of ways that utilities are starting to get smart and asking for more of data centers that are looking to interconnect.
Thanks for clarifying that, Spencer. I feel like it's actually a really interesting new challenge in the industry. And we hear a lot about data centers bringing their own power. Does this change if data centers have on-site generation to skip the utility completely?
No, so it turns out that when facilities choose to bring their own power, they expose themselves to many of the exact same problems that a utility would face. When these variable AI loads are passed back either to gas turbines or reciprocating engines, oftentimes they can excite resonance in the actual spinning machines themselves, which can cause mechanical failure in shafts or bearings. For example, in a reciprocating engine, perhaps the response time is a little bit faster. Just the action of the governor trying to seek a different operating point every 30 to 40 seconds can cause massive engine hour accumulation. So for those engines which are able to track that kind of variable load, there's significant fatigue. And then there are certain power generation setups that simply can't track the load. For example, a fuel cell, which has a time constant, 10 minutes or longer, even when hot. And so battery storage is really essential to perform that load smoothing function between the data center and prime power. And it actually serves even more of a smoothing role when you integrate renewables on site as well.
All right. So given that battery storage is definitely going to be an essential part of the future of AI data center buildouts, how much storage are we talking about and where does it go?
Yeah, it's a really important question. And the truth is that there's not just one answer because there's not just one type of data center. In this ecosystem, we have training data centers and inference data centers. Some of them are grid connected. Some of them have their own on-site generation. Some of them are incorporating renewables. Some of them are not. Some of them are grid connected and have on-site prime power. And they all have different reliability requirements and different power distribution architectures, especially as we start to look at the early transition from AC distribution inside the data hall to DC distribution. So the right amount of storage depends on a lot of factors: where the prime power is coming from, the reliability of that power, and then also the types of restrictions related to ramping or intermittency that you need to accept in order to interconnect to that power source. But in general, there's a spectrum here. So there are some data centers which will be able to operate with a minimal amount of storage. Think perhaps 5 to 10 minutes worth of storage, which is about the same amount that they've traditionally had in a UPS system. But that storage will have to be much more rate capable and will have to be able to cycle for many more times in order to perform the smoothing function. There are other data centers which, for reasons of integrating renewables or connecting to the grid on a flexible interconnection, may bring hours worth of backup battery. And in fact, we see now some data centers which are bringing enough battery that they don't even need to have on-site diesel generators at all. And this actually speeds up the construction of the data center. They don't have to wait for scarce backup diesel gensets. and they don't have to apply for air permits. So there are lots of benefits to bringing hours worth of battery storage when the site can permit it.
Fascinating. So I want to ask you a question I'm sure is on many people's minds. What would your advice be for battery companies looking to target the emerging market for AI data centers?
Yeah, so I talk to a lot of battery companies that are placing significantly more attention on this market now than they were maybe 6 months ago. And it's not hard to understand why, because it's growing more quickly than any other battery segment. And individual purchase orders can make a company's IPO, right? An individual facility can have gigawatt hours of storage. It's a highly competitive market. Some of the best battery players are setting their attention on this market. And so it's important to understand that. But what's exciting about it is that there are so many niches to fill. Because no two data centers are exactly alike, because they all face slightly different power challenges, and they all have the willingness to pay to solve them, making a bespoke product for the right customer is an opportunity in this space, unlike in many others. There are many different types of opportunities. There's opportunity for energy dense backup that looks more like perhaps what was in a traditional UPS. There's opportunity for battery technology with extremely long cycle life that can be deployed to help perform the smoothing function. There's opportunities for very low cost battery storage to help speed up time to power when interconnecting with renewables, and then everything in between. So there's a tremendous amount of opportunity, but I would say first, know your customer, understand the requirements, and then find your niche. And that's where we've been fortunate to do a lot of work with players in this space. And if you're thinking of targeting the data center market, absolutely encourage you to reach out to us, reach out to me for discussion on how you can do it.
Spencer, I think that is great. We've dug into some very real challenges here, but you've also discussed some very interesting opportunities. And so I think that is the perfect place to wrap up this conversation with you today. It's been great to learn from you. I really, truly appreciate all of your insights and strategies to help business owners navigate this ever-evolving landscape. So thanks again so much for your time.
Yeah, thanks. It was great to be here.
Absolutely. And for our listeners out there, if you'd like to learn more about what Spencer and the team at Roland Berger Americas are working on, visit www.rolandberger.com. And if you're a fan of this show, please share it with your colleagues. And of course, be sure to follow us on Apple, Spotify, or Podigy.